All right, this is video, obviously there's a typo, 7.4. And we're going to solve logarithm equations and inequalities. You're going to notice that they mimic the exponential functions and equations and inequalities with similar properties. Now you have to know your radical rules, you have to know your exponent rules and fraction rules, and of course logarithm rules. So let's jump right into our video, our notes. So our vocabulary is logarithm equations and logarithm inequalities. Of course, our objectives are here. We're going to solve logarithm equations and logarithm inequalities. Okay, so let's get back into our book. So what's a logarithm equation? It's just an equation that has a logarithm in it, correct? And we can use the definition of logarithm to help us solve them. For instance, example 1. We basically are going to change from a logarithm to an exponential form. So let's look at that example. So the example says solve log base 36 of x equal 3/2. Well, without a calculator, it's kind of hard to solve this. Or we can say x equal 36 raised to the 3/2. Okay, well, we have exponent rules. We know that 36 is 6 squared. Yes, raised to the 3/2. Now we are going to use the power of power rules that says we multiply the power of x. So 2, it's got no fraction, times 3/2 equals 6 cubed, which gives us our answer of x equal 216. No brainer, pretty easy, yes, because it was a perfect root. Or we could have put this in our calculator if it wasn't. We could have gotten an estimated and rounded it to whatever place value. Now let's look at the properties. So if we move down to our property of equality for logarithm functions, it says if you have b, if b is a positive other than 1, then the log base b of x equals the log base b of y if and only if x equal y. So we had this with exponents, right? If our bases were the same, then those were equal if and only if the powers were equal. Here, logarithms, if you have a log on the left and a log on the right, they're equal if and only if they have the same base, they're equal if and only if their arguments are the same. So let's look at example 2 that tells us solve log base 2 of x squared minus 4 equals log base 2 of 3x. Now remember, I said it was really important to be able to identify our argument. This is our argument and this is our argument. We have two logs, one on the left, one on the right. Do they have the same base? Yes. So these are equal if and only if the argument's equal. Now I can say x squared minus 4 equals 3x. I can solve using algebra. And we notice we have a quadratic, so we're going to have to factor this, x minus 4 times x plus 1. If you need help, see me later and we can talk about this. So x equal 4 and x equal negative 1. Now we put this back in. Now look at this. If I put negative 1 in here, it's never going to be negative because it's squared, correct? But look at this argument. This would make this log base 2 of 3 times negative 1, which would make my argument negative. And we said, can our argument ever be negative? No. So we don't use that, and we only test 4. So we'll test 4 in there and make sure that we have a true solution, and it works because if we put them in here, log base 2 of 12 equals log base 2 of 12. And we can't put it in here because our argument can be negative, so we throw that answer out. So it's kind of like an extraneous solution, but we don't call it extraneous. It's not a solution. All right. Now let's look at logarithm inequalities. What is a logarithm inequality? It's just an equation with an inequality sign and an inequality equation with a logarithm. Okay. So we're going to use the same property for logarithm functions. It says if b is greater than 1, and x is greater than 1, then log base b of x is greater than y, then x is greater than b to y. So we just put it in an exponential function. Now, however, look at the less than. If you have b is greater than 1 and x is greater than 0, so x is positive, we're saying log base b of x is less than y, then x is greater than 0 but less than by. So we're just taking this and making an inequality. So let's look at example 3. Example 3 is also an inequality, but we're going to do example 3 and we're going to do guided practice. So it says solve log base 3 of x greater than 4. So we're just changing it to an exponential function. So that goes away. You say the argument x is greater than 3 to the 4th. 3 to the 4th is 81, so x is greater than 81. Okay, so that's when you have a greater sign. What if you have a less than sign? Look at guided practice 3b. It says solve log base 2 of x less than 4. Well, again, you're going to change it to an exponential, so x is less than 2 to the 4th, x is less than 16. However, it has to be greater than 0 because x can't be negative, correct? So because it's an inequality and we have a range of solutions, that's why we have to add that greater than 0. Okay, now let's look at the next one, the properties. So we have a property just like we did for the equal sign. It says if we have two logs, one on the left, one on the right, and b is greater than 1, the base, then the log base b of x is greater than log base b of y if and only if the arguments x is greater than y, and vice versa. If you have a less than sign, then x is less than 1. Why? So let's look at example 4. They want us to solve this. Now, this is where we have to remember things about our bases and our arguments, what they can and cannot be. So if we want to solve log base 4 of x plus 3 is greater than log base 4 of 2x plus 1. I have an inequality. I have log on the left and log on the right. Are my bases the same? Yes. What are my arguments? X plus 3 and 2x plus 1. So the property says this argument, this log is greater than this log if and only if x plus 3 is greater than 2x plus 1. Now we use algebra to solve, so I minus 1 minus x, and I get 2 is greater than x, or basically x is less than 2 is my solution. Now, I have to look at my arguments. Remember, my argument cannot be negative, so I need to find when is it defined, just like a radical. So it's undefined when x plus 3 is less than or equal to 0. It's defined when the argument is greater than 0. So I'm going to do x plus 3 greater than 0, and I'm going to do 2x plus 1 greater than 0, because we said it can't be 0 either. So we minus 3, that's where it's different from a radical, as we would have the equal sign here because it can be 0, but an argument cannot be 0, nor can it be negative. So x is greater than negative 3. X is greater than negative 1/2. I'm not doing the algebra. You can do it. You can pause the video and do it. Make sure you get the same thing if you're not sure. Now I'm going to draw a number line. I'm going to put these values. So I've got negative 3, negative 1/2, and 2. It says x is greater than negative 3. Let's do a different color. It says x is greater than negative 1/2, and x is less than 1/2. And where do they overlap? Between here and here. So x is going to be greater than negative 1/2, but less than 2. So you have to find out when it's defined, because that it will be undefined when the argument is negative or 0. All right, do the practice problems, and we'll see you in class.